Again, welcome to CS 113, which is Mathematical Structure for Computer Science, also known as Discrete Mathematics. Again, in these lectures, we're going to discuss about Boolean Algebra. And our first part of this lecture is what is a Boolean Functions. So our main objective is to go through what is a Boolean Algebra. Then we're going to discuss about Boolean expressions and also Boolean functions. Also, we are going to talk about the identities of Boolean algebra and also the abstract definition of a Boolean algebra. So let's start with the introduction to Boolean algebra. Here we say a Boolean algebra has a rules for working with elements from the set 0 and 1. So in Boolean algebra, all the variables can have only two items or two values. Either the variable value will be 0 or 1. Unlike our regular algebra course, mathematics course, a variable can be any value. And actually, we use the decimal numbering system from 0 to 9. So we have 10 digits. In Boolean algebra, we have only 2 digits, 0 and 1. So a Boolean algebra has a rules for working with elements from the set 0 and 1 together with operators. And operators can be Boolean sum, or Boolean product, which we use the dot in the middle, Boolean product. Then also we have the complement, which will be our bar on top of a variable or a value. So a sum is the same as a sum we do in an arithmetic operation. But here we should put in mind we have only 2 digits, 0 and 1. Unlike a regular algebra where we have a decimal numbering system, we can have 9 plus 2 or 20 plus 40 in a digit. The digits are from 0 to 9. Complement means if it's yes, the complement of yes will be no. If it's true, complement of true will be false. So in Boolean algebra, the complement of 1 is 0. The complement of 0 is 1. So let's go through the example here given to us about operators. So in the Boolean sum, we can say 1 plus 1 is equal to 1. You can see here we didn't say 2, because as we said earlier, the Boolean algebra uses only 2 digits, 0 and 1. So I cannot say 1 plus 1 is 2. There's no 2 digits in the Boolean numbering system, or we use the term binary numbering system. So 1 plus 1 is 1, and also 1 plus 0 is 1, and 0 plus 1 also is still 1. Then 0 plus 0 is 0. In a Boolean product, we say 1 times 1 is 1, but 1 times 0 is 0. 0 times 1 also is 0. 0 times 0 is also 0. So again, Boolean sum is a little bit tricky here. 1 plus 1 is 1. And also 1 plus 0 is 1. And also 0 plus 1 also 1. Then 0 plus 0 is 0. In a Boolean product, 1 times 1 is 1. But 1 times 0 is 0. 0 times 1 is 0. 0 times 0 is 0. Now the complement means 0 complement will give us 1. Or 1 complement will give us 0. So let's see an example here. They say we should find the value of 1 times 0 plus 0 plus 1 complement. So the first thing I'm going to do is the parentheses. So 0 plus 1 will give me 1. We have the rule here, 0 plus 1 is 1. So 0 plus 1 will give me 1. And remember, 1 complement will give me what? 0. 1 complement is 0. So that means everything here, 0 plus 1 complement, the answer will be 0. Then we know that 1 times 0 is what? 0. 1 times 0 is 0. So the answer here will give us 0. So here we can see 1 times 0 is 0. Then 0 plus 1 is 1 with the complement. Now 1 complement will give me 0. So 0 plus 0 is 0. Now, with this, the Boolean expression is also a Boolean functions. We know a function always have a variable. A function always have a variable. So here we say the definition for a Boolean function. Let's assume b equal to 0 and 1. So b is our set, which consists of 0 and 1. So now b to the power n means how many digits I have. But all these digits will be a combination of only 0 and 1. So b to the power n means I have variable from s1 to sn. N is the number. So if it's b to the power 3, it means if the variables represent x, then it will be s1, s2, s3. So here we say b to the power n means the variable s1 up to sn, in that si will be from 1 to n. Si belongs to the b. For 1, I should be what? Less than or equal to n and greater than or equal to 1. So if it's 3, then we go from what? From 1 to 3. If it's 100, then from 1 to 100. So this will be, again, I is from 1 to n. And again, the n will be the number of elements we have. Let's say the number of elements in a set. So here we say is the set of all possible n tuples. And these variables can only be zeros and 1. So here we say let b be 0 and 1 items. B to the power n will be s1 all the way to sn, where s1 to sn, which we represent as si, belongs to b. For I is from 1 to n. Is the set of all possible n tuples of zeros and ones. So here we say the variable s is called a Boolean variable. So s is a Boolean variable, and a Boolean variable can only have 2 digits, either 0 or 1. If it assumes that the variable only from b, that is, if it is only possible values are 0, as we said, 0 or 1, a Boolean variable possible values can be only 0 and 1. A function from b to the power n to b is called a Boolean functions, and then the degree is n. So if it's b to the power 3, then it's a Boolean function with a degree of 3. A degree of 3. So example, the function f xy equal to s from the set of other pairs of Boolean variables to the set 0, 1 is a Boolean function of degree 2. Y degree is 2. We have sy. So this is the possible values we can have. If I have the xy, 2 variables, their possible combination will be 1, 1, 1, 0, 0, 1, then also 0, 0. So here we say fx and 1 can be 1, 1 is 1, 1, 0 is 0, 0, 1 is 0, 0, 0 is 0. This will be a product. So let's see this example. Hopefully this may help us a little bit. So for example, I have a Boolean function f, and I have a possible 3 variables. But the expression is xy plus z invert. First, I'm going to count how many variables I have. It's 3. So if I have 3 variables, and normally we call this the truth table, the possible combination will be 8, because it will be 3, will be the, as we saw it earlier, b to the power n. So n is the number of variables. So if the variable is 3, b always will be 2, because it's a Boolean. Possible value is 0 and 1. So 2 to the power 3 will give me 8. So the possible combination we can see here is exactly 8. 1, 2, 3, 4, 5, 6, 7, 8. So we get 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, then 0, 0, 0. So construct, they gave us expression here. And the expression here for the Boolean function, the function have three variables, s, y, and z, and it's s times y plus z invert. So since the variables are three, I came up with 8 combination because it's 2 to the power 3. And if the variables are 4, it will be 2 to the power 4, which will be 16 possible. So here is 8. So the first thing I'm going to find is the xy. So since s is multiplied by y, I will look 1 times 1 is 1. 1 times 1 again is 1. 1 times 0 is 0. 1 times 0 is 0 again. 0 times 1 is 0. So we can see that the rest of the values all will be 0. Because we get 0 times 0, 0, 0 times 0 again, 0. 0 times 1, 0 times 1, 1 times 0, 1 times 0. So everything will be 0. Now, when we get the sy finish, we add it to z invert. But since we know that z is given, we can find the z invert. So when z is 1, the z invert will be 0. When it's 0, it will be 1. When it's 1 again, it will be 0. When z is 0, z invert is 1. When z is 1, z invert is 0. When z is 0, z invert is 1. When z is 1, the z invert is 0. And the last one, when z is 0, z invert again is 1. So now I know the x, y, and z inverse, so I'll add the two together. So 1 plus 0 is 1. 1 plus 1 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 1 is 1. So this will be our truth table. So in the final exam, we may have a question that they say find the values of a Boolean function representing this. And now the solution we use a table with a row of each combination of the value s, y, z to compute the values of, again, f, the function s, y, z. The goal is to find these values here for the expression sy plus z invert, and that's our solution. Or sometimes the question will be given that find the truth table of the Boolean function f x y is equal to s times y plus z invert. So the truth table will be everything. So again, take a note, this question can be a final exams. Find the values of the function expression, or find the truth table of the function syz equal to sy plus z invert. Either way, the solution is this. So Boolean expression and Boolean function, we continue here. We have the definition saying that a Boolean function f and g of n variables are equal if and only if f with its variables b1 up to bn and also g have the same variable b1 to bn. So if I have two functions, a Boolean function f and g, they can only be equal if their variables size is the same and also the values of the variables also is the same. So here that's why we have function f with the variables b1 to bn equal to g, function g, with the same variable b1 to bn. And here we say whenever b1, b2, and bn belongs to b, two different Boolean expressions that represent the same function are equivalent. So we have two different, but they are representing the same function. Then the complement of the Boolean function f is the function f with the bar, where f bar have its variable from s1 to sn, is the same as f s1 to sn or complement. So here we say let f and g be a Boolean functions of degree n. Again, degree n is the number of variables. The Boolean function f plus g and the Boolean product f times g are defined by the following. So we have f plus g. So we get f plus G S1 to Sn equal to F S1 to Sn plus what? G S1 to Sn. The same thing with the product. Since F times G from S1 to Sn, we can say, okay, F from S1 to Sn times G from S1 to Sn. So this example give you how many different Boolean functions of degree n are there. So how many different Boolean functions of degree n are there? We can start from beginnings. We say by product rule for counting, there are 2 to the power n different n tuples of 0 and 1. Always the base will be 2, and the n is the number of, again, variables we have. So because a Boolean function is an assignment of 0 or 1 to each of these different n tuples, by the product rule, there are 2 to the power 2n different Boolean function of n. So the example tells us that there are 16 different Boolean functions of degree 2. We display this in table 3. So here we can see we have x and y. So possible combination is 4. 1, 1, 1, 0, 0, 1, 0, 0. So F1 can give us, if it's addition, 1, 1, 1, 0. F2 is addition, 1, 1, 1, 0. And then let's keep going. So next is the identity of Boolean algebra. We mentioned that this is very, very important. We have to know these identities, and these identities will help us to solve Boolean expressions. So for example, I know that if I have a S complement and complement, 2 complement, they will cancel each other. So S complement will be X. This is called the law of double complement. Now I know S plus S always will give me X. Why? Because X values are only 2 possible digits, 0 and 1. So 0 plus 0 is what? 0. 1 plus 1 is what? 1. So which means whatever the value is X, if you had the same value, you should get the same answer. So 0 plus 0 is 0 if S is 0. If S is 1, then it will be 1 plus 1, which is also 1. With the product also the same thing. Because if S is 0, we get 0 times 0 is 0. And if S is 1, it means 1 times 1 is 1. Now next we can say we have S plus 0 is X. Why? Because 0 doesn't matter. If S is 1, it will be 1 plus 0 is 1. If S is 0, 0 plus 0 is 0. So S plus 0 always is X. Then the same thing, S times 1 is always X. Because if it's 0 times 1 is 0, 1 times 1 is 1. So whatever value is the X will give us the result. The same thing applies to the next one. We have S plus 1, the answer is 1. Because if S is 0, is 0 plus 1, 1. If S is 1, 1 plus 1 is 1. But S times 0 should always be 0. Why? Because if S is 1, 1 times 0 is 0. If S is 0, 0 times 0 is 0. 1 times 0 is 0. So that's why we have this identity. Now the commutative law is changing the variable, so position. So if I have S plus Y, it's the same as saying Y plus X. Or if I have S times Y, it's the same as saying Y times X. It's just changing the variable position. Associative laws also is in arithmetic operations. If I have S plus parenthesis Y plus Z, it's the same as S plus Y parenthesis plus Z. If you change the location of the parentheses, the answer is the same. In this example, we have X parenthesis YZ. It's the same as saying XY parenthesis times Z. It's the same. Then we also have a distributive law, which is a little bit different from arithmetic operation. You see, we have X plus YZ. So this distribution will be S plus Y times S plus Z. So S plus YZ gives us S plus Y times S plus Z. Here it's the same as arithmetic operation concept. S times y plus s times z. 6 parentheses is multiplication. This is our De Morgan theorem. If I have sy or invert, we can invert individually. So S invert, now we have a product, is S times Y. Product invert will give us plus. Plus invert will give us product. So that's why here we have plus S invert plus Y invert. Because SY or invert will give us, individual invert will be first invert X, S invert, multiplication invert to give me addition, then y invert to give me y invert. The same thing applies to the multiplication also. So we get S invert, now addition becomes multiplication, then y invert. And also this is called the absorption loss, very important, we use it a lot. If I have x plus xy, y value doesn't matter, but s always will determine, because the only possible y value we can get either is 0 or 1. So this means if s is 1, the answer will be 1, because whether y is 0 or 1, we still get 1 at the end. Because if this expression sy is 0, 1 plus 0 is what? 1. If it's 1 plus 1 also is what? Still 1. So the s will determine the result. Now the next one too is the same thing. I have s times s plus y. Now the y doesn't really matter, because if s is 0, everything is 0. If s is 1, because I have 1 here, 1 plus y, which is 0 or 1, will still give me the same value for the x. So the answer will be x. And the last is the unit property. S plus s invert will be 1. Because remember, invert. If it's 0, then it will be 0 plus 1. If it's 1, then it will be 1 plus 0. So the answer always will be 1. So these are, again, the Boolean identities, which I think very, very important in this, our algebra, Boolean algebra topic. So there's an example given here. They say we should show that the distributive law, x, parenthesis, y plus x, close the parenthesis, is the same as sy plus sz. Yes, it's the same, because this will be distributive. S times y plus s times x. But here we have x, is supposed to be x. But now let's see, now they say z. If it's only x, it's easier to validate. But they say sz, so we don't know. Let's use the truth table to see. So how many variables I have is 3, because this is z. So we have s, y, z, the possible 8 combination. So the first thing I'm going to find is to find, actually this is supposed to be z. Supposed to be x, y plus z equal to sy plus xz. So this is z. So you can see first we find y plus z. So we had the y plus z here. 1, 1 is 1, 1, 0 is 1, 0, 1 is 1, 0, 0 is 0, 1, 1, 1, 1, 0 is 1, 0, 1 is 1, 0, 0 is 0. Then I know I have xz, so I do the xz multiplication. 1 times 1 is 1, 1 times 1, 1 again, 1 times 0. Again, we can see x and y column, the first 2 columns. 1 times 0 is 0. So everything here is 0. We have 0 throughout. So 0 throughout. Then now we know the xy, xz also the same thing. Take x and multiply by z. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 again is 1. The rest will be 0. 1 times 0 is 0. Everything is 0, so the rest will be 0 throughout. Now we know we have sy, xz, we have y plus z. So now we can find s times y plus z. And that's what we have here. Then sy times plus xz. I have sy plus sz. So 1 plus 1 is 1, 1 plus 0 is 1, 0 plus 1. Then the rest here 0 plus 0, 0, 0. So everything will be 0. Then I have the x times y plus z. So 1 times 1 is 1, another 1 times 1, another 1 times 1 is 1. So we have 3 ones. Then 1 times 0 is 0. Actually, from here, we know everything is 0. So the answer will be 0. Here we are doing again addition. But both of them are 0 here. So everything is 0. So sy is 1 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. Then the rest 0 plus 0, 0 plus 0 throughout. So when we look at the answers here, we can see that they are the same. The output is the same. So this means s times y plus z parentheses is the same as sy plus sz. It's the same. So these are some of the formal definitions of a Boolean algebra. We say a Boolean algebra is a set B with 2 binary operations. The binary operations will be, the symbol here means disjoint, which is or, and conjunction, which is again, is and. The element can be only 2, 0 or 1. We also have a unary operation, which is complement or not. So again, or means disjoint. Then conjunct is the and. The possible element, 2 values, 0 and 1. Then we have this is a binary operation. With the and or, we need 2, as we can see here, x or 0, x and 1. So we need again 2 binary operations. And then unary means we complement only one variable at a time, say x complement, y complement. So here we are saying that a Boolean algebra is a set B with 2 binary operations, or and n. The element can be 0 and 1, and then unary operator, the complement, says that all the x, y, and z is in B. So we saw the identity laws. X or 0 is always x because all means plus. If s is 0, 0 plus 0 is 0. If s is 1, 1 plus 0 is 1. So that's why it's x. We are repeating almost the previous identities, but this time we are using the symbol. So instead of saying plus, we use the or disjunction. Then this is n will be product. So s times 1 is x. Then we have s or x invert, which will be 1. Because again, the v, which is or, is plus. Then opposite, upside down v is the n, which is multiplication. So now let's look for some examples here. They say find the values, if any, of the Boolean variable x that satisfy this equation. S times 1 is 0. Now, since we know from the rule that s times 1 is x, this tells me that s times 1 is 0 only if x is 1. I mean, s is 0. If s is 0. Because s times 1, the answer will depend on x. If s is 0, then 0 times 1 is 0. If s is 1, 1 times 1 is 1. Since here is equal, we write since s times 1 is s, the only solution is s equal to 0. Now let's look at b. S plus x is 0. This is also possible only if x is 0. So we say since 0 plus 0 equal to 0 and 1 plus 1 equal to 1, the only solution is again if x equal to 0. Again, this is binary. The variables can have only 2 possible digits, 0 or 1. Then C said s times 1. It says, yeah, that's true. Because since this is multiplication, if s is 0, the answer will be 0. If s is 1, the answer will be 1. So we say since this equation holds for x, there are 2 solutions. If s is 0 and also if s is 1. Now the next question says, since neither x or s invert must be 0, no matter what s is, there's no solution. So this is D. If s is 0, s inverse should be what? 1. So the answer will be 0. If s is 1, s inverse will be what? 0. The answer should be 0. So s times s inverse can never be 1. So here, since we say either s or s inverse must be 0, no matter what s is, there's no solution. Now let's do the second exercise. They say we should use the table to express the value of each of these Boolean function. So here this is almost like the previous example we did. We have a function with 3 variables, s, y, and z. So this means the possible combination of the truth table will be 8. So we have 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0. And it's 1, 2, 3, 4, 5, 6, 7, again, 8. Because again, it's 2 to the power 3. Now, the expression we are looking for value is s invert x. So here I will say, okay, s invert, it means x is 1, it will be 0. So 0 times 1 is again 0. And here, all the answers here will give me 0 because from 1 is 0, 1 is 0, 1, 0, so 4 zeros. Now here we get 1. 1 times 1 is 1. Here give us 1. 1 times 1 is 1. The last two will give us 1, 1. But y is 0, 0. So the answer will be 0. So finally we get 0, 0, 0, 1, 1, 0, 0. The second question is the same. How many variable? 3 again. So we have 8 possible combination. Now what I'm looking for is s plus yz. So y times z is 1. 1 plus 1 is 1. Y times z is 1 times 0 is 0. 0 times plus 1 is 1. Because we get y times z then plus x. So for example, here 0 times 0 is 0. 0 plus 1 is 1. Then here also, we have 1 times 1 is 1. But 1 plus 0 is what? 1. Now 0 times 1 is 0. 0 plus 0 is 0. 0 and 1, we get again the same thing. It's multiplication. So we get 0. Then 0 plus 0 is again 0. Then 0 times 0 is what? 0 again. Times 0 and plus 0 is also 0. And the same thing applies to C and D. So C, we are looking 3 variables and we are looking for x, y invert plus s, y, z or invert. So the first thing I'm going to do is to find the y invert. Y invert will be 0. And I know 0 times 1 is what? 0. Then let me find the x, y invert. So first of all, s times y times z will be 1 times 1 times 1, which is 1. Then the whole 1 invert is 0. So you get 0 plus 0. That's why the answer is 0. The second one again, we have s already, but we need y invert. Y invert is 1. So y is 1. So y invert will be 0. So 0 times 1 will be 0. Then s, y, and z, the answer will be 0. Then 0 because it's multiplication. So 1 times 1 times 0 is 0. 0 invert will give me 1. Then 1 plus 0 is 1. So that's why we have 1 here. And let's do the last one. Then again, we leave the rest. So here, I have y is 0. Y invert will be 1. So 1 times 1 is 1. So since we have a plus, it doesn't matter. If this is 0, 0 invert is 1. 1 plus 1 is 1. If it's 1, 1 invert is 0. 0 plus 1 gets still 1. So that's how we have to do all the rest. Same thing applied to D also. So D, since we have 3 variables, we have 8 possible combinations. The variables are S, Y, Z. So the same thing, let's leave S aside first. Find Y, Z. 1 times 1 is 1. Then Y invert, Z invert is 0, 0. 0 times 0 is 0. Then 0 plus 1 is 1. And then S is 1. So 1 times the last S1 will give me 1. So that's why our first value is 1. Now let's see why the second expression is value is 0. Again, we have YZ. So Y times Z is 0. So this is 0. Y invert is what? 0, because it's 1, so it's 0. And since it's multiplication, then everything here will be 0 again. Now, if I have 0 plus 0 is 0, and S is 1, 0 times 1 is again 0. And we have to do this throughout. So let's try the second or the third one. We have YZ again, 0, 1. 0 times 1 is 0. Then we have Y inverse Z invert, which will be 0 again. And then we have S is 1. So 1 times 0 plus 0 is 0, and 1 times 0 is 0. So that's why third one we have 0. Then exercise 3, they say what values of the Boolean variable X and Y satisfy SY equal to S plus Y. So the solution will be either they are 0, 0 and also 1, 1. Which means, for example, if S is 0 and Y is 0, 0 times 0 is 0. 0 plus 0 is also 0. Or if both of them are 1, 1. So 1 times 1 is 1. 1 plus 1 is 1. Then the question is, so what values of Boolean satisfy the condition? Now, if S is 1 and Y is 0, then 1 times 0 will be what? 0. But 1 plus 0 will be 1. So we get 0 equal to 1, which is false. So the only way this condition will be true, SY is the same as S plus Y. Both SY must have the same value, either 0, 0 or 1, 1. And they say here we should verify the associative laws. Here they give us S plus parenthesis Y plus Z, or S plus Y parenthesis plus Z. So associative laws means we taking one of the changing one of the variable in the parentheses. And we should get the same answer. So since here I have Y plus Z, I find the Y plus Z first. Here we have S plus Y, so I find Y, S plus Y. Then I'll add it to Z. Here I'm going to add it to X. The answer should be the same. The same. For product also, the answer will be the same. So another example, find the duals of these Boolean expressions. So the A, S plus Y, the dual will be S times Y. Because here we say in each case, we simply change each 0 to 1 and then vice versa, and change all the sum to product and then vice versa. So if I have S plus Y, I will change the plus to multiplication. Here B, I have complement, S invert, Y invert, or complement, multiply. So I'll change it to addition. And here I have S times Y times Z, so it will be S plus Y plus Z. S invert times Y invert and Z invert, so it will be S invert plus Y invert plus Z. And the last one, since I have S times Z invert, then it will be S plus Z invert. Since this is addition, it will become multiplication. And then we get X plus 1. We change this to plus, and this is to 0, 1. And then S invert, this is multiplication, become plus, then 1 becomes 0. So this will be the conclusion of our Boolean Algebra Part 1. Here we talk about Boolean identities, and we saw some few examples. So again, wish everybody the best. Thank you.